So today we're going to talk about bond dissociation energies. And bond dissociation energies are useful because it will allow us to look at systems that we may not have actual experimental data gathered on, and we can predict enthalpies of formations. So one of the first things we want to do is we want to think about bond making versus bond breaking. So if we were to consider a bond, so we have two different atoms that are bonded together. In order to separate them, we're going to have to overcome this attraction, which is in the chemical bond. So this is going to cost energy. So anytime that we're talking about a bond dissociation energy, what we'll see is this value is always positive. So now what we can do is we can actually look at both the reactants and the products, and we can try to determine the enthalpies of formation or the enthalpies of reactions given these bond dissociation energies. So one of the things I do want to point out is that we will use a similar equation as whenever we were finding delta H of reaction. There's one slight difference, and to the best of my knowledge, this is the only type that we'll encounter like this. So anytime we see that we're looking for a difference, a change in every other unit, we would always look at products minus reactants. Well, this is the one exception that we'll cover where we actually take the reactants minus the products. So, for instance, if we were to look at this sample reaction right here, so this is a dissociation reaction. We have compound XY dissociating to form X plus Y. If we wanted to find delta H for this reaction, we would take the bond dissociation, which we represent with a D, of XY minus the bond dissociation energy of the products. Well, here the products are lone atoms. So what does that mean? Well, there's no bonds. If there's no bonds, that means there's no bond dissociation energy. So delta H would actually just be equal to the bond dissociation energy of XY in this case. But keep in mind, whenever you are breaking a bond, it costs energy and it's positive. But if you are making a bond, you are going to release energy. So let's go ahead and look at a few examples here. So the strategy for this, whenever we're going through, is to always try to go through and draw a Lewis structure if possible. And then from there you'll count up the number and types of bonds, and then you can refer to a chart, which I've given a link here, and you can look at the different bond dissociation energies of your compounds. So for instance, let's look at this example. We're looking at the formation of hydrogen. So here we have two hydrogen atoms coming together to form H2. Well, if we were to draw this in the Lewis structure, we have a hydrogen atom, we have a hydrogen atom, and then in our products we have this hydrogen molecule. So notice that in our reactants, there's no bond. So there's no bond dissociation energy associated with these lone hydrogens. In fact, since we're only making a bond in this reaction, what we should see is that the delta H should be negative. So let's go ahead and try this out. So recall from the previous slide that we'll take the dissociation energy of the reactants minus the dissociation energy of the products. So since we have two lone atoms, this is 0, minus the dissociation energy of the hydrogen molecule in our products, so that's minus 436 kilojoules per mole. So we would end up with a delta H of reaction for this as negative 436 kilojoules per mole. So far, I've only given you cases wherever we have lone atoms that are combining or lone atoms that are being formed. So let's go ahead and try an example whenever we have reactants and products with bonds. So for instance, in this particular example, we're looking at the formation of ammonia from molecular hydrogen and molecular nitrogen. So let's go ahead and draw the Lewis structures for all of these. So H2 looks like this, single bond between the hydrogens. Ammonia has a triple bond, with each nitrogen having a lone pair. Nitrogen has a triple bond between the two nitrogens. And then ammonia is nitrogen with 3 single bonds, 2 hydrogen, and then a lone pair on the nitrogen. So what we're going to have to do is we're again going to take the dissociation energy of the reactants minus the dissociation energy of the products. In previous examples, we only had one reactant or one product. So now we have to think about how many total bonds there are. So in this case, we have in our reactants 3 hydrogen-hydrogen bonds plus 1 triple bonded nitrogen. That's all we have in our reactants. Minus in our products, well, how many NH bonds do we have? Well, if we go through and count, in our Lewis structure we have 1, 2, 3. So we have 3 NH bonds per ammonia molecule, and then our coefficient is 2, so we have a total of 6 NH bonds. So now what we can do is, I've already pulled these values from the table for us, is we can just plug in the bond dissociation energies of hydrogen, nitrogen, and then NH. So what this would look like is we're going to end up having delta H is equal to 3 times 436 kilojoules per mole plus 1 times 946 kilojoules per mole and I try to put my reactants and products in brackets to make sure I don't make a silly error with my order of operations. And I'll subtract off my products, which would be 6 times then the bond dissociation energy of the NH bond is 390 kilojoules per mole. And once we plug this all in, what we should end up finding is that delta H for this reaction is equal to negative 86 kilojoules per mole. Well, experimentally it's been measured that it's actually negative 45.9 kilojoules per mole. Keep in mind that that is for the formation of 1 mole of ammonia, and here we have 2. So if we go through and divide this by 2, delta H for a single mole is actually negative 43 kilojoules per mole. So although there is not 100% agreement with experiment, this is a great method for being able to draw Lewis structures and try to determine what an enthalpy of formation is, especially if it's a system that you cannot obtain a measurement on. So that concludes our lecture on bond dissociation enthalpies. I hope this helps you out.